So friends, welcome back. After completing our differentiation course, we are now starting our integration course. Now first, suppose we have a situation, we have an equation given here in this sense that we have 1 by 2 plus 1 by 4 plus 1 by 8 plus 1 by 16 plus up to infinite terms is 1. It looks strange, but it's true. What is strangeness? Strangeness is that the sum of the never ending series ends somewhere. That means the sum of a series which has infinite terms which never ends, but the sum is finite. Second thing is that the sum of the all terms after a particular term is equal to that term. Means after suppose 1 by 2, after 1 by 2 if you take the sum of all the terms 1 by 4, 1 by 8, 1 by 16, it is equal to 1 by 2. Similarly, after 1 by 4 if you take all the terms, its sum is equal to 1 by 4. So the thing is that these two things are strange. Now how to convince ourselves that such a case is possible, Now let us take two illustrations. Suppose a person moves from A to B and the distance from A to B is 1 meter. So one way of understanding this scenario is that the person has moved from A to B and the distance is 1 meter. Another way of understanding the same thing is that while going from A to B, the person must have crossed sometime the midpoint of A and B, and that is a C. So from A to C, it has moved a distance of 1 by 2 meter. Now, after that, the person must have moved the midpoint of C and B, and that is D. So it must have moved extra distance 1 by 4 meter. Again, remaining distance is D to B, that is 1 by 4, and it must have crossed its midpoint E, that is equal to 1 by 8 meter. Similarly, the person would have be crossing or traveling half of the remaining distance each time, and therefore the number of terms is infinite, but sum of all the terms would be finite. Second case is that suppose we have a square of side 1 and 1. So one way of getting the area of this is that we have 1 into 1 and that is equal to 1. So area is equal to 1. Another way is that suppose we are taking that we divide this area into two halves. So this is 1 into 1 by 2 and that becomes 1 by 2. First term is 1 by 2. Now again for the remaining area we divide it into another half. So that will equal to 1 by 2 into 1 by 2, that is equal to 1 by 4. Now whatever the remaining area we divide again this into 1 half. So this would become 1 by 2 into 1 by 4 and that is equal to 1 by 8. Again we divide it into two halves, remaining into two halves. So that is equal to 1 by 8 into 1 by 4 into 1 by 4 and that is equal to 1 by 16. Again 1 half, again 1 half. So finally we are zeroing on to the last area, that is a dot, that is the infinite term, but the last term is tending to 0, but the sum of the all term should be equal to 1 in this way. Now how to find the area of a circle? Let us find area of the circle. We divide this circle into a number of small thin rings using a pen of thickness dr. So we take a pen whose thickness is dr and we draw rings, circles of thickness dr one by one. So after that what we do is that we would get many rings shown by these shaded places, these shaded areas. Now what you do is open these areas and place it here. Open this area and place it here. Open this area and place it here, like that. So one by one we are placing areas. So after this dr, the sum of all these thickness would be equal to r, and the first term would be equal to, the first ring would have a perimeter or you can say length, shaded length, that is equal to 2 pi r, and this is decreasing. Now if you draw a dotted line here, you are going to get almost area of a triangle. This area of the triangle would be equal to half into base into height, that is equal to pi r squared. See, half into 2 pi r, first strip into this. But is this area of the triangle or area of this sum of these shaded parts? Now the thing is that this is the area of the triangle. The area of the shaded part is slightly less than this because these errors due to red corners, missing red corners is missing. So you may argue that this is not the area of the circle, it is area of the triangle, and there is some difference between the area of the circle and area of the triangle. Okay, that's okay. But if we make the pen thinner and thinner and thinner so that these missing errors are smaller and smaller, then we are going to approach towards the value of the area of the circle. So this is one of the methods we can get it. Okay, suppose we can say that yes, in spite of that, you can argue that even if we go for a smaller and smaller thickness of the pen, we would never reach the value of the area of the circle. And that is so because we do not know the value of the pi even, because pi is a non-repeating, non-terminating decimal number. So what we are saying is that approximately we are zeroing on to the area of the circle. We may not reach there, but who wants to reach there? So another way to get the area of the circle of radius r is to draw a regular polygon in which this circle the circumscribes the regular polygon. That means this circle passes through the vertices, all the vertices of this regular polygon. Suppose we have an n-sided regular polygon. In that case, if we see the area of the polygon would be equal to n times the area of the polygon would be equal to n times the area of the triangle ABC, the triangle OAB. So in that case, that would equal to n times of area of the triangle would be area of the triangle half into r sine 2 pi by n, half into r sine 2 pi by n. So that would become equal to n times of r square by 2 sine 2 pi by n. But this is not equal to area of the circle because these red portions are missing. These red portions are missing. This summation of the total polygon area is slightly less than area of the circle. But if we continue to increase the number of sides of the polygon, then this error area is less and less. So difference between the total area of the polygon and the total area of the circle decreases as number n becomes more and more, and under the limit n tends to infinity, we can say that area of the polygon becomes approximately equal to area of the circle. So we are going to see now that differentiation is the division of a smallest dy by dx with small y by small x, that gives us finite value. Integration gives us the sum of the infinite terms, and that can be finite. The sum of infinite terms, and all the terms are very small. The sum of infinite terms and all the terms are small would become finite. A good outcome is that the formula wise, very good outcome of all our discussion would be that the formula wise integration is the inverse process of differentiation. That means if fx on differentiation gives gx, then gx on integration should give fx. So that makes our mathematics a bit easier. Now let's go to the integration to realize the power of the sum of smallest quantities in finite number. So we are going to realize the power of the small divisions, and their sum would give us something that is very good.